Now our starting point for the next step is going to be this slide, where we observed that there is something called the strain energy function, and we've observed in the context of linear elasticity that when I take the derivative of that function, I get the stress, which is linear in the strain, because that's what linear elasticity means. And when I take the second derivative, it has to be a constant because it is linear elasticity, and that constant is a fundamental material property, which is in this case the Young's modulus. Now, we are going to move into the next step. And now we will try to think about the basic idea of doing modeling for nonlinear elasticity. So let's say basic idea. Okay. So now the first thing that I am going to propose, which it turns out makes sense, is the following. Now, at large deformations, in other words, nonlinear, okay, elastic deformations. Nonlinear meaning when we observe experimentally that the relation between force and deformation is not a line anymore, just like we did for that simple rabbit skin experiment. Large nonlinear elastic deformations, we're going to admit that the stress is again calculated by the relation that we have expressed in the last slide. Namely, the stress is going to be calculated from the derivative of the strain energy function, or a strain energy function more correctly, with respect to the stretch. So that is a crucial statement. Now, when we were talking about anisotropy, and I mentioned the reason why you expect the compliance or the stiffness matrix to be symmetric. Remember, it has to do with the fact that if you take a structure and load it in any way you wish in the linear regime in particular, and then you expect when you unload, you want to recover all the work input that you had initially put into the structure. If you want to recover all of that, then the compliance and stiffness matrices, therefore, they have to be symmetric. That's a requirement that's imposed by the physics from what we understand from elastic deformations. The same thing goes here. In this experiment, if I have very, very large deformations, so first of all, let's agree. There is a relation between stress and force and deformation. Therefore, when I calculate the area under the curve, that will be always the amount of work that I input into the structure as I deform. And when I unload, I recover some of that work. Now, if it turns out I recover all of the work, then by definition, I'm talking about elastic deformations. And so if I want to write a relation for stress such that it indicates elastic behavior, in other words, stress times incremental deformation, that's going to be incremental work. I sum those works up, those work quantities up, and then when I unload, I keep decreasing that work. I have work output from the structure, and overall from the deformation, from a cyclic deformation, I should recover zero net work because that's what I expect, right? So I have an expression for the stress. I do the cyclic calculation of the work. I expect zero. For that to happen, it turns out that at any instance, the amount of stress has to be related to the amount of energy stored per unit volume as such. Stress is something I can measure. Amount of work per unit volume is something I can calculate. It turns out stretch likewise is something I can measure. There has to be such a relation between these quantities. Otherwise, when I try to predict the amount of work done by a certain stress expression, theoretically over a cyclic deformation, load and unload, the amount of net work done will not be equal to zero, and that doesn't comply with the idea of elasticity. So that is ultimately, it turns out, a requirement on which we can rest in the context of elasticity in general, whether or not we have small deformations, and that's a physical requirement. Good. So now that we have already observed in the context of linear elasticity, but here we're stating it with this verbal, let me say, proof for large deformations. Now, on the other hand, now the question is, well, what is so the outstanding question that we have is, what is this function psi? Now, that's not a trivial question. You might say, well, okay, the material will have a Young's modulus, and therefore I can write psi to be, well, what we just proposed in the previous slide, which was that. Now, however, if you write that, then you can take the derivative of that with respect to stretch, which is going to define stress always, and the second derivative of that will be a constant, and therefore the relation between stress and strain will be a constant, or stress versus stretch. And that defines linear elasticity. But what I want to describe is nonlinear elasticity. Therefore, what I've concluded is, if psi is quadratic in the stretch or strain, therefore, then what I can describe with that is only linear elasticity. So if I'm talking about nonlinear elasticity, the stress versus stretch or force versus displacement curve does not have a constant slope. It changes. For the rabbit skin, it continuously increases. So that means when I take the second derivative of the function with respect to stretch, it's not going to be a material constant anymore. It's going to be something that changes with deformation, and therefore probably it's going to be a function of the stretch itself, which suggests that this function is something that's more than a quadratic in the stretch. Has to be so if this is supposed to be a non-constant. So at this point in class, what I would like to do always is ask you, well, so now we understand that psi should not be a quadratic function of stretch. Now, first of all, let's discard linear stretch, because linear stretch would, if we just have proposed a linear expression for strain energy function in terms of stretch, you take the first derivative of that, you get the stress. Stress is a constant, irrespective of deformation. So linear function psi with respect to lambda, it's meaningless. It has to be at least quadratic. At least linear elasticity should be described. So I would ask, well, so it's not going to be quadratic, it's going to be more than that, but what, right? And then you would come up with certain forms. So let me draw a line here, because at this point, really, most of the input would come from you. So I'd like you to think about that question by pausing the video, if you like, for a while. What can I propose for the form of psi such that the stress is more than a linear function of the stretch, so that the derivative of the stress with respect to stretch, or the second derivative of the strain energy function with respect to stretch, is more than a constant. Okay, and this way I can describe nonlinear elasticity. And so then you would propose certain expressions. Now what I'm going to do is, if you've thought about that question, I'm going to summarize some of the things that you typically propose. Now, for instance, you would propose that, that it should be perhaps a cubic function. Why not, right? Because if it's quadratic, let me correct this. If it is quadratic, it doesn't work. It has to be at least then maybe a cubic function of lambda. Does that work? Now, you will propose a lot of different functions, but common to all of them is an observation that has to do with the shortcomings of possible proposals. So, for instance, if I take that one and plug in lambda equals 1, what does that mean? Lambda equals 1 means stretch of 1, in other words, strain of 0, no deformation. Well, if there is no deformation, what do I expect about the amount of energy that's stored per unit volume? It should be 0. So I check this function, whether it delivers 0 energy stored per unit volume at no deformation. But this function predicts that it should be 2. right? Which is strange. So this is not equal to 0. It's not quite something I like, okay? So I want no energy stored if lambda equals 1, okay? It's just something that we'd like to have. It turns out it's not a big necessity. Certainly it is physically pleasing to have it. Now, there are other types of functions that you would propose. So among these, an exponential is a very nice example, because the slope of an exponential would rapidly change. And let's propose an exponential form, e to the power lambda. Okay, so just like with this one, with this function as well, actually there are several shortcomings. I'm just highlighting one among several, but it gets us to think about the important factors that govern our modeling efforts in the context of nonlinear elasticity. So what I'm going to highlight in this case is I'm going to highlight the stress, which is going to be a function of lambda. How do I calculate it? Remember, always through that relation. So now this is always valid, whether it be small or large deformation elasticity. And the derivative is going to be simply e to the power lambda, the same function. Now, let's think again. Well, if there is no deformation, in other words, when strain is 0 or lambda is equal to 1, what do I expect about the amount of stress? Well, I expect no stress. That is not only something that's pleasing to have, that is a requirement. But in this case, sigma of val at lambda equals 1 is actually equal to a, and it's not equal to 1, right? So it turns out that you can try to capture certain characteristics about the stress versus strain behavior, in particular load versus stretch. It's going to rapidly increase. It looks like an exponential form, in particular in the example, rabbit skin example that I gave you. This exponential is a very, let me say, good actually idea. But there are shortcomings in the form of the strain energy function that I proposed. But once I have a good path, a hint at what I'm supposed to do, and that's a good hint, I can always go back and make corrections. Now, so for instance, in this case, we can build upon this idea by correcting the shortcomings. And so we go ahead and modify what we perceive as a weakness in our proposal. We modify to meet physical expectations. Okay. And those physical expectations are, for instance, that the stress should be 0 at lambda equals 1. So what kind of stress form would be suitable for that? If I had a to the power, a multiplying e to the power, not lambda, but let's say lambda minus 1. I'm just going to propose one form and show you that it actually works. Suppose I had that form instead of like this. So sort of still an exponential, a constant, but to the power lambda is replaced by that, and then there is a minus 1. And now I notice that if I substitute lambda equals 1, this is going to be 1 minus 1, 0. Sigma 1 is now equal to 0, as I expect it to be physically. Now, however, to be consistent with what we have done, we need to make sure that we modify psi also properly, so that the derivative of psi delivers the stress as a function of lambda. And it turns out that the form of psi that is consistent with the stress in this sense is equal to e to the power lambda minus 1 minus lambda. So you take the derivative of that and you will recover that stress function. And at one shot, I've actually already also corrected the form of psi, because now if you plug in lambda equals 1, here the value of psi was not equal to 0, but here it is equal to 0. So I've corrected it immediately with the expression for stress. Now, moreover, now let's have a look and notice something peculiar here. Now, first of all, there is a parameter here that appears A. Now everything else, there's actually only one other variable here, which is lambda. It just is dependent on the amount of deformation that I impose. It's not something I can pick. It's imposed, it's given to me, and I'm supposed to calculate the stress. And you'll see in our upcoming discussion that eventually we have data, we want to fit that data. And as we've discussed before, for instance, specifically in the context of the discussion on models for plasticity, we had some free parameters. We determined those based on our data. So in this case, we may want to ask, well, what is A? Okay, so now first of all, this is a relation between stress and strain, which is valid at large deformations. But what if I impose tiny deformations where the stretches are extremely small? When the stretches are extremely small, the material displays a line as stress-strain relation, and the slope of that line is the Young's modulus. So notice, first of all, when I take the derivative of sigma with respect to lambda, which is the second derivative of psi with respect to lambda, I get a e to the power lambda minus 1, which certainly is not a constant. But if deformations are small, this thing, in the limit lambda going to 1 or epsilon going to 0, this thing is going to vanish. And the slope of the line is going to be A. So at small deformations, the slope is almost a constant, which is equal to A. But I know that the stress-strain relation is linear and the slope is E at small deformations, and we conclude eventually that A is supposed to be actually equal to the Young's modulus. This is again a physical requirement that you would actually come up with yourselves in our in-class discussion. So what you've just invented, by the way, is called, in this context, or it's very intimately related to something that's called the Funk model. It's one of the famous models, initial models of biomechanics for soft tissue. Now, by the way, I'm always mentioning this topic to be nonlinear elasticity, which is somewhat fitting with our terminology, but a more suitable name, especially when I write this relation, is called hyperelasticity. And I'm just stating that for your reference in case you want to look into this matter further on your own. But now we want to continue a little bit further because so far we haven't really done any modeling. I'm motivating a series of steps that will eventually be useful for us.